Hi everyone, and welcome to this, which is the first webinar in our 2017 series. My name is Tom Pritchard and I'm the host for today's session. I'll be introducing you to our speakers shortly and also rounding up at the end. Today's webinar has the title Delivering Better Geotechnical Designs with LimitState GEO, and it will explain how LimitState GEO can be used to improve the workflow and influence your geotechnical designs. You'll also find out a little bit about the technology behind the software and see how it's applicable to a wide range of different situations. The main section of the webinar will run for about 45 minutes until about 1:15 p.m. UK time, and there should be time for a few questions at the end, which can be posted at any time during the webinar via the question functionality that's present in the interface in front of you. We do try to get around to answering as many of the questions that you send in as we can, but given the amount of time available, we can't always get around to all of them. We do, however, follow up on anything that's unanswered after the webinar is finished, so if you do find you have some specific questions regarding the software, then don't worry, we will get around to answering those for you as well. You can also contact us outside this webinar via info@limitstate.com, and we'll be happy to answer any of these in detail for you. So without further delay, our speaker today is Dr. Colin Smith, who's the LimitState GEO Product Manager, and I'll now pass you over to him.
Thank you, Tom. As mentioned, my aim today is to give you an introduction to how LimitState GEO can be used to simply and easily model geotechnical problems. We'll be looking at workflow, the software, how it can be used to conduct what-if type calculations, and a quick look under the hood, how it works. To this end, I'll primarily be using the software directly to illustrate the key points, but I'll make use of a few slides, beginning and end, for an introduction and summary. As this is a short presentation, the main aim is to give you a flavour of what the software can do, and there won't be time to get into the details of the software functionality. However, there'll be time at the end for questions. So first, I'll give you a little bit of background to LimitState. So the University of Sheffield has been conducting research into limit state analysis and design and the use of optimization in civil engineering for almost 2 decades now. And the company, LimitState, was spun out from the university in 2006 with the aim of making this research available to industry via a range of innovative software products. LimitState focuses on tools for ultimate limit state analysis. So to put this in context with other currently available software, on the one hand, the top left here, we have sort of generally easy-to-use software and spreadsheets that are based on conventional hand calculation type methods that can handle a specific problem type. Whereas on the other, on the bottom right here, we have the more complex finite element software, which can deal with pretty much any problem geometry and much more complex soil behavior. And there's a gap between these two ends of the scale, and we feel filling the gap is computational limit analysis. So this provides the geometry and flexibility of the finite element method with the ease of use and simplicity of traditional methods. The only parameters you need are cohesion, friction angle, and unit weight, essentially. And we can take this approach of geotechnical engineering and the same approach with arch bridge analysis, concrete slab analysis, and so on. So such an approach allows the software to determine the collapse state for any problem geometry, so we're able to model slopes, footings, retaining walls, structural elements, soil reinforcement, as illustrated in some of these animations. And we get similar flexibility in our other products, so we have LimitState Ring for solving masonry bridge analysis problems, LimitState Slab for concrete slab analysis. And these products are used across the world by a wide range of companies, large and small. So anyway, that's enough introduction. Let's try out the software. So we're going to start at looking at how we can solve a relatively simple problem from start to finish, and this will be a retaining wall example, essentially this extension of an embankment using a stem wall. So the problem we have is we have an existing embankment. It needs to be widened. We know how high the embankment is and what the strength of the soil is and the weight. In order to widen it, due to space restrictions, we're going to use a stem wall and backfill that with granular material, and the widened embankment is to take additional loading. So the question is, how wide or big should that stem wall be? And the fill we're going to place is going to be stronger than the existing embankment, angle of friction of 34 degrees compared to 27 degrees for the embankment. And we're going to have some variable loads or mixed range of loads, a higher central load and slightly lower side loads up there. So slightly complex setup. Now, if we're going to do this by a sort of traditional hand calculation approach, we might put a virtual back on the retaining wall here and then use perhaps Rankine's earth pressure theory. However, that is complicated by the fact that we don't have a uniform surcharge, so we don't know so easily what the relative contribution of the different loadings are. It's also complicated by the fact that we have this interface between weaker and stronger material. It's not clear whether that earth pressure distribution is going to be influenced by the presence of the weaker material behind. Alternatively, we could look at a Coulomb wedge type analysis, try different wedge angles. That might be more appropriate, and those wedge angles can go into the backfill, into the existing embankment as well. But this type of analysis is pretty tricky to do by hand, and it's quite easy to make errors in it. So, if we wish to solve this using the software, we can start with a DXF drawing or a CAD drawing of the layout and import that into the software. So that's what we're going to do. So we're going to take this diagram, put it into software, and see how that works. So I'll just start up a new instance of the software. So this is what it looks like when you start it up. We've got various buttons along the top and side, various functionality, which I'll explain as we go along. Something called a property editor here, which displays properties of items in the problem, and a materials explorer here, which displays the materials that are available for use. So I'm going to start by using the import function, import a geometry, and I'm going to import our DXF file. Now the import utility allows you to change the move the coordinate system if you wish. We just take it as is. So that's our geometry comes in. Now it may come in with some additional construction lines. I'm just going to clear those so that we're left with the core geometry that we want. Now we can't solve that as it is because we need to tell the system what sort of soils we've got. Now, we might not have initially a detailed site investigation of this problem. Maybe we're just trying to do a scoping calc to see whether a stem wall is feasible. So we might have a rough idea of the materials we have. On the left here, we have the default materials in the software. So these are sort of generic materials with the sort of typical properties for these types of soils. They're not intended for sort of final precision use, mainly for scoping, but you can define any material type that you like or material properties. So I'm going to assume that we've got maybe a very stiff clay down here, and I can just drag and drop the materials onto the model. And I'm going to use a firm clay for the rest of the fill, just to keep this simple. And I have a concrete here, which I'll just use for the stem wall. So we've got our problem geometry there. We need some loading. I'll just put in one load just to illustrate how that's done. So I can click on this upper boundary. Its properties appear on the right here. We've got a property of loading here, so I'm going to put in a load. And I'm going to put in a variable load with a normal force of 10. And so let's now put a load in here. And I might think, yeah, I can run that now. So to solve a problem, we simply click this button here, solve, and it says error, no support has been applied. So we get some helpful diagnostic information about the problem, which we could look through. But basically we've got no boundary conditions, so we have to set those. So I can just click on these boundaries. If I hold my control key down, I can click multiple boundaries. And I see the properties of those boundaries appear here again. What I'm interested in is the support type. Anything I click on here, we get a little window down here, explains what that property is, so that should help navigate the software very quickly, and there are always usually typically hyperlinks to the manual for more detailed information. Anyway, here we just want to set a fixed boundary, So that gives us fixed at the side. We fix on that side, and we'll fix these boundaries as well. We should be able to solve. So I click solve, and very rapidly the software identifies the critical collapse mechanism and shows me collapse load there. So we get an animation, helps you visualize, understand what's going on. We get a solution which is called an adequacy factor on applied load of 17.54. If I click on that, get a little dialog, and that tells me exactly what that means. So essentially it says I've applied this variable load of 10. It's not had any factors, Eurocode type factors applied to it, but in order to cause collapse of this system, it needs to be multiplied by that number 17.54. So I have this value in order to cause collapse. So this 17.54 is essentially a factor of safety on load. Okay, so that shows you how you can set the problem up. Actually, I want to set the problem up with the parameters that I showed in the slides earlier on, so I'm going to close that and just pull up the version that I've already generated. So this is a model already prepared, and this gives us the setup that I showed. So again, anything I click on in the problem should appear in the property editor over here. So if I click here, this tells me some details about nodal spacing, which we'll explain later. It tells me the material in it. Its existing fill has the strength 27 degree friction angle and 18 degrees unit weight, which is what was defined on the slide. And this material here is a granular fill that has the angle of friction of 34 degrees. And all these values here are editable, so they're very easy to change. And in addition, we can set interface properties. So if I click on this band here, this is the interface between the base of the concrete wall and the granular fill there, and we've set this to be a special granular wall interface material, and it has 0.75 or 3/4 of the strength of a parent material, which is the granular fill itself, which is what we have underneath. So anytime we change its properties, the interface automatically follows to suit. Now, we're going to run this analysis. We've got all the loading up here. We've got the loading here of 10, and then 45 in the middle here, and so on. And we're going to solve this under Eurocode. So what we've set here, we have a scenario manager, and in this we can select various partial factor applications. So here I've selected Eurocode 7 Design Approach 1 Combination 2, and that will automatically apply factors to the loads and the material properties before the analysis is undertaken. And that's most likely to govern failure. We could do the design or analysis based on that, and then eventually we can check it under DA11 afterwards if we wished. So if I run the problem again, I just click the solve button. Software very rapidly finds the critical failure mechanism and tells me that I've got an adequacy and load of 0.77. So anytime I get an adequacy less than 1, it means a problem is unstable. Something has to be reduced in terms of load, or a material has to be made stronger to get me a safe result. So if I click on here, it basically tells me that these characteristic values I had here, they're scaled up by the DA12 factor 1.3, and then they're multiplied by this 0.77. So these are the values that would cause collapse, but they're lower than the design values. Therefore, this does not comply with the code. So we've got a little bit of a problem there. The current design isn't going to work well. We can play around, do some what-ifs and see what's happening. One thing we can observe, if I click this animate button again, we can see that it's sliding down the interface between the current fill and the old embankment. Of course, that old embankment is weaker. Be interesting just to get a feel for how big that effect is. So I can click there, drag the material back, so I've got more fill here, rerun the analysis. So now the failure mechanism does not involve the previously existing embankment, and my adequacy factor has gone up to 1.117. So now it's higher than 1. This does now comply with the code. So clearly that interface is a problem. or is contributing. But we'll put it back. So this button up here is undo. It just undoes my previous actions. So ideally we don't want to have to excavate the original embankment away. Maybe there are other ways of dealing with that problem. So we'll try a different approach. We've decided to put this wall on our granular fill. If we could use a stronger fill, say the original basal deposits here and here, these have a strength of 40 degrees. Would that work? So if I put that there, I can replace that. I'd also have to replace this interface material. So what I'll do is just create a new material here. We create what's called a derived material, which is derived from a parent material. I'm going to call this basal wall interface. Oops. Interface. Give it a suitable color. Its parent material is going to be the original basal deposits, and we're going to ask that it models it with 3/4 of those properties. So I click OK. That then appears here in the property editor. I can drag and drop that, put it on there, replace, and now I've got that correctly modeled. So again, I can click Solve, run through the analysis, and we get a somewhat simpler failure mechanism. This time it's pure sliding. There's no bearing failure in the soil underneath the wall, and the adequacy factor has gone up to 1.8. So that again is complies with the code. So that would be one way of dealing with the issue, but maybe we don't want to do that. That material may be hard to get hold of or too compact to that sort of strength. So I'll just undo those changes and we revert back to our original setup. And if we look at the current failure load, which is lower than 1, we're getting failure down here. So maybe we can try and suppress that by adding in some extra fill. So I've got, if we zoom in here, I actually put a small amount of fill there. What I'm going to do, just for speed and simplicity, is just drag that up to about there. So we've now got some extra fill there that might just be enough to suppress that failure mode. Solve that problem, see what that does. And now we can see that having put that weight in there, it's suppressed the base failure and just causing a sliding failure, and this factor has gone up above 1. So that would be an alternative method of getting us to comply with the code. Perhaps that's the solution we want to go with, but maybe we're concerned about flooding, that we may get a significant rain event, might actually flood the base of this. What effect could that have? Well, we can add in, for example, a water table here. Let's stick it just above the sort of ground level. You can draw inclined water tables or other ways of setting water pressure. This is the simplest one. I'm just going to enable the water here. So now we have a water table here, and again I can analyze the problem and just see what effect that water will have had on the solution. And that's brought the adequacy factor just below 1, so it's just on the point just of not complying with the code. So again, if that was a concern, we might wish to do something additional to clarify or improve the margin of safety on this. Okay, so that I hope has given you a flavor of how we can very easily explore a problem, change parameters, change materials, and see how we can get towards a design that would comply with the code. So we'll jump back to the PowerPoint and just look at some other types of what-if analysis. So here we're going to look at a very simple slope stability problem. So this is an example from textbook by Whitlow. Nice simple problem, 20-meter long slope, 10 meters high, the soil of a C-5, angle of friction of 30, unit weight of 20. Sort of simple slope stability analysis. Method of slices gives a factor and strength of 1.6. And if you're doing method of slices, you require to tell the program what the assumption of the interslice forces is. Typically you have to specify entry-exit points and center of rotation. So there's a lot of extra control or data you have to feed in to do this kind of analysis and some assumptions. With the software, if I pull up the relevant model, there we go. This is the same geometry, and we have the same strength 5 and 30, unit weight of 20. No need to worry about entry-exit points, interslice forces. We just click solve, and it will give us a factor in safety and strength. And the collapse mechanism, which is very similar as was identified by the method of slices, and we get a factor of 1.63 here, very close to that 1.6 by the method of slices. You'll see that what we used here is what's called a factor strength model. The software has two modes. The mode we've been using for that previous example of the embankment was factor load. We were looking at how much bigger loads had to be to cause collapse at the surface of the embankment. Here we're saying how much do we have to reduce the strength of the soil by to get collapse. So I'll just solve that one again. And again, if you click on the solution here, you get a dialog which tells you actually what's happened. So the software has taken the strengths of the soil, it's applied, in this case, unit partial factors, and then in order to get the system to collapse, it's had to divide them by 1.6. So that if the system will collapse when the strength, the C' and the phi' values have reduced to these values. And so that gives you the factor of safety on strength for this particular problem, which is analogous in general terms to the factor of safety you get from a method of slices approach. Now again, you've got the flexibility to ask what-if questions. We could put a load on the surface here, for example, and just say a little bit more. So you can see we can apply permanent, accidental, or variable loads. We can also declare whether they're unfavorable, favorable, or neutral. Neutral isn't actually a Eurocode designation, but it's a default in the software for where the user has not actually specified what it is. So I could put up here a variable load of 5 kilonewtons per meter squared and ask the software what difference does that make to my solution. So it finds this factor on strength, we get 1.61, and actually it's made very little difference, and you can see the mechanism has only intersected part of that load, so it's really not contributing. It's the self-weight of the soil that's having the biggest contribution in this case. Sometimes with slope stability analyses you might have pre-existing slip surfaces. That's very straightforward to put into the model. I can quickly draw one in, fairly straight one, but I can draw in extra lines into the problem. If I want it slightly curved, I can add a vertex and drag that down. So I could add more in and make this more curved. And then I could say, well, this boundary has a weaker material. Just for simplicity, I'll take this soft clay, drop it on the boundary like this. So now I basically have a weak pre-existing slip surface in here. I can solve the problem, and you see it's now saying yes, the critical mechanism is to slide down this interface, and the factor in safety on strength has dropped from 1.6 down to about 1.16 through the presence of that slip surface. So again, we can model internal weaker zones or layered soils. I could, for example, change the strength of this underlying material to something completely different, and we could have a layered soil in some sense, and again I could solve the problem and it would take account of that automatically. Right, we'll now move on and look at a problem involving foundations. So again, I'll take another example model that I've already set up. So here we have a very simple foundation sitting on the surface of a soil. The footing soil has a undrained strength. We're going to model this as an undrained problem of 70 kPa, unit weight of 20. This is just a rigid material, and we're applying a load here. Now this load is being applied as a unit load. We've actually got a half here, but the reason why I've put in a half is that this load is actually, its geometry extends. If we look down here, we get its geometry, that line extends from -1 to +1, so it's 2 units wide. If we apply a stress of a half to that, that gives us a unit load 1 kilonewtons per meter. We have a property here called adequacy is true, and this is telling the software we want you to multiply this load, find out what you have to multiply this load by to cause collapse. So we have that sat on this clay soil, and we also have a surcharge here which is defined as a permanent load of 10, but we haven't put adequacy on that. That's just a dead load, if you like. This is your kind of live load. Now, the other thing I want to just show here, we looked at Scenario Manager briefly before. We can set multiple scenarios up. So here I've got 3 scenarios up. I'm asking the software to solve a problem with no partial factors applied, just to get a feel for what happens there. To then apply the Eurocode 7 Design Approach 1 Combination 1 factors. So those are primarily factoring up the loads before the analysis is undertaken, and the Design Approach 1 Combination 2 factors, which are primarily factoring down the strengths before the calculation. So it will do all 3 at once. So if I click Solve, it'll run through all 3 of those, and we actually get the same mechanism for each because it's an undrained problem, but we get the 3 solutions here. And as you'd expect, with unit partial factors, we get the highest load capacity, 711, and Design Approach 1 Combination 2 gives us the lowest one. So if I click on there, we can see that we have this value of a half. Because it's a permanent load, it gets factored by 1, and then it needs to be multiplied by 502 to cause collapse. So we're actually using the software here to tell us how big a load we could actually get away with, rather than the margin of safety on a real actual structural load. What we'll do now is just look at a slightly different variant. So this sort of analysis you could easily do using Terzaghi's bearing capacity theorems and formulae, and you don't really need a piece of software to do that. But you may come across situations where you have a foundation that's buried. It may be that you've got layered soil, or the soil is changing its strength with depth. You may have a slightly asymmetric problem, and then it's much harder to use those standard formulae. So here we've got a slight added complication in that we've got a buried footing. Now there are ways of using Terzaghi's formula to deal with that, but if you want to account for the strength here and here, it becomes slightly unsatisfactory to start using depth factors. We can also, in this model, I've actually set it up to model a gradient in strength. So we've got an undrained soil, and I actually said that the strength of the soil is increasing by 1 kPa per meter depth here. We could set that to any value we like, and that's to start at an elevation of 2, which is actually at this level here. So if I click here, this starts at an elevation of 2. I can actually preview that to see what's happening with the strength. So I've got a preview strength button here, click short term, and that shows me that the strength is increasing with depth. If I hover over here, you can see I start at 70 up here, and as I go down, the strength goes up only slightly in this particular example to 73 at the bottom of this particular model. So I can click Solve. Again, we're solving the 3 partial factor sets, and we'll click on this load. Now in this case, I've set the surface, the load on the foundation to be variable, so with the factors DA12, our characteristic values are half, multiplied by 1.3 to get 0.65, and then the software says, well, you have to multiply that by another 518 to give me 336.76, which will cause collapse to this particular problem. You may also encounter issues where the load isn't coming vertically on your foundation. Again, that's can be a bit tricky to deal with using standard bearing capacity formula. So for example, here I have a variable load of a half normal. I could add a horizontal component of 0.2, for example. So now we're inclined and we can look at how that analysis works. And this time it's telling me that I will collapse at a slightly lower load of 390 and I get a different mechanism off to the side. Now in fact, because it's a clay soil, the footing is dragging the soil with it here, and if we want to allow tensile failure, we can add a tensile no tension cut-off material to the boundary. I add that on, so now we've got a combined materials here that allow no tension as well as an interface shear. And if I analyse that again, we get a somewhat simpler failure, and we can now allow tension cracks to form, and as we'd expect, we get a lower failure capacity in this particular case. And again, if geometry changes, for example, if that was to be a bit lower, we would get a different mechanism and a different collapse mode, and the software will automatically take account of that. So that takes me through most of the demonstrations I want to go through, or we have time to go through. What I'd like to finish off with is to explain how this software works. Now you'll see that when we ran the solutions, a lot of little dots appeared on the problem, and these are nodes that populate the problem, and when we solve, what the software is doing is finding slip lines that connect up these nodes to find the critical collapse mechanism. So we'll just briefly run through how that all works, because it's obviously very important. If you use any piece of software, you know how it works underneath so you can get the best out of it. So how does it work? So the method is a relatively new numerical method called discontinuity layout optimization. It was the outcome of a 5-year EPSRC research project at University of Sheffield. The key method was published in the Proceedings of the Royal Society in 2007. And essentially, it's a simple linear optimization problem that is easy to solve with modern linear optimizers. So I can illustrate pretty quickly in 4 images how the core method works. So here we have a very simple problem. We have a rectangular block of soil with fixed boundaries to the left and the base, and a load to the surface. Instead of populating it with, or dividing it up into elements as in a finite element approach, we populate the domain with nodes. So here I've got 12 nodes, 4 by 3. And we connect every node to every other node with potential slip lines. So that is in total 66 possible slip lines in this case. And then we use optimization to pick out of that set of slip lines the critical set that give us the collapse mechanism that dissipates the least energy. So that's going to be the critical collapse mechanism. So in this case, out of those 66 slip lines, we've picked out 6. Now clearly the accuracy of this method will go up as you increase the number of nodes. So in the model that I've been illustrating in the first part of this presentation, I've used quite a coarse distribution of nodes just for speed. But normally we would solve with more nodes. So typically you might be solving 1,000 or 2,000 nodes, which means of the order of 1 million connections, and out of that the software will very rapidly pick out the critical 10 or 20 or 30 slip lines that form the critical collapse mechanism for that problem. Then what the software does is once it's found those critical slip lines, it's able to put those together to identify solid blocks and then animate those to assist in the interpretation of the model and what sort of collapse is going on. So how accurate is this? Well, we've applied it to many benchmark problems. This is a classic Prandtl punch problem. The solution is known to be 2 plus pi. Well, you get to that within 1% in approximately less than a second with the software. And a very useful feature of the software is that it identifies singularities in the mechanism without difficulty. That's something that can often challenge finite element approaches that need to use mesh refinement to deal with that. The software, it's just inherently dealt with, no special programming, and these singularities or fan zones turn up quite often in limit analysis problems. We verified the software against a wide range of closed-form solutions. Every time the software is updated, it automatically runs 1,000 tests or more to check that it's still doing what it should do. Over 100 of these are displayed on the website, so you can go and look at these and check how they compare with benchmark solutions in the literature. There's also quite a large number of academic publications written using the software, so you can find this bibliography on our website, and it's around 50 publications using the software for a whole range of applications: foundations, slopes, reinforced soil, etc. Just to wrap up, showing you a few other little examples of how you can use it for gabion walls, footings next to trench, working platforms. You can model sheet pile walls, we can model bending failure in those, key walls, pipeline interaction, slope stability problems, and so on. So to wrap up, I hope you've seen that the workflow with this software is very straightforward, from geometry import to reporting. Actually, I neglected to show that reporting. We'll come back to that later if we have time. I hope you found the user interface very intuitive, puts you in control. You can solve with one mouse click, and it's very easy to handle partial factors. It's very interactive, so a lot of our customers use the software to answer what-if type questions, get a good feel for a problem, see what's controlling stability, and so on. And that you can use one piece of software to solve any ultimate limit state problem type, so you no need to impose idealizations or correction factors for non-standard geometries, or to learn how to use many different programs. So I will wrap up there, and we have some time for some questions. Okay, I'm just reading through the questions. Okay, so I've got a question: where the water table is above ground level, does the software allow for the unit weight of a free body of water in the analysis, or does the water body need to be modelled explicitly? The answer is yeah, the software does deal with that directly. So if I draw in a water table like that, the water pressure is automatically modelled acting on the surface, and it correctly takes account of the effective stress equation, so the effective stresses at the surface will still be zero. So that is inherently dealt with. There's no need to explicitly model the water pressure as that. Okay, for slope stability, I've got a question here. Using Eurocode 7, the unit weight of the soil can be favourable or unfavourable depending on the geometry. How does the software deal with this? So this is a big area of debate with slope stability. Is the soil favourable, is it unfavourable, or is half of it favourable, half of it unfavourable, depending on the nature of the mechanism? The software, unless you specifically tell it, will just treat that entire soil body as either favourable or unfavourable. I think generally Eurocode 7 tries to avoid this issue by pushing you towards design approach 1 combination 2 or design approach 3, where you factor favourable and unfavourable permanent loads by 1 in either case. So that kind of gets around the problem. If you need to factor them separately, then it's really up to you. You can split the problem up if you wish. If I just go back to that slope problem, in fact, in this problem, all the soil is unfavourable because we don't have a toe failure. But if we felt that part of it was unfavourable, we could split the body of soil and tell this body of soil that it's favourable, for example, while the other body is unfavourable. So it gives you the flexibility to deal with that, or you may use the principle of the single source, that the entire thing either has to be favourable or unfavourable, but you can set the weight of the material as favourable or unfavourable in addition to the loadings here as being favourable or unfavourable. Okay, got another question about the effect of boundaries on the determined solution. Does the software detect if a boundary is affecting the solution, i.e. the vicinity of a boundary to the critical failure mechanism? So that's a good question. So in this particular case, if I bring this, okay, if I go for a clay problem here, I think what I'll find is, no, I'm still solving it in drained mode here. What I need to do is flip this from a long-term analysis which does drain parameters to a short-term analysis which uses undrained parameters. I get a mechanism which effectively hits the boundaries. So if these boundaries are essentially artificial, then you're just hoping that's a domain that's big enough to capture the mechanism, then clearly this problem is affected by these boundaries. And the software will not inform you of that because those boundaries might be genuine. It might be bedrock down here, for example. So you need to just look at the mechanism that's detected, and if you see that and you know that these boundaries, for example, are not real, but supposing this is really bedrock down here, then we need to we can drag these outwards, or we can actually type the values in here. So dragging is a little bit imprecise here. I've got -5, so I could go -10, -10 on the geometry of this edge, and extend that, and then rerun the problem. And now I'm not getting the intersection here, but it's still happening back at this level. So again, I need to pull that back and rerun. Now the boundaries are not affecting the solution, assuming this is genuine bedrock or a much stronger material at the base. So yes, you do need to look at the whether the mechanism is intersecting the boundary to check whether that is affecting the analysis. And we will see that this adequacy factor has gone, we finished up with 3.63. It hasn't made a huge difference, just slightly bigger, 3.64 and 3.7, with those boundaries being further in. And it very much depends on the nature of the problem as to how big an effect those boundaries have. I've got one more question. Can we vary the nodal density within a soil to focus in on a failure mode? So yes, and in fact we did use that for actually, if I open up the stem wall problem. So in fact, if I preview nodes, you may have spotted that I've actually put more nodes under the foundation or the wall than behind the wall, because I'm expecting quite a lot of failure in there. And this is controlled by, when you click on the body, you actually get to control the nodal spacing here and here. So here it's 0.25, here it's actually 1/2, and here it's 1. So you could distribute the nodes as you wish to give you to capture the more complicated failure down there. So if we run this, you can see there's more complicated failure down there. You can also increase the total number of nodes in the problem using this button. So here we have basically coarse is 250 nodes, medium will give us 500 nodes, and we get a lot more nodes in the problem. And generally we recommend you check the effect of the number of nodes in the problem, just as you would with the number of elements in a finite element software, in order to look at the accuracy. Okay, I think we're out of time there, so thank you very much for listening, and I will pass back to my colleague Tom just to